Okay, so given a vector field F, a scalar function F is a potential for F if the following holds. If F is equal to the gradient of F. In this case, when F is equal to the gradient of some vector field, we say F, the gradient of a scalar field, we say F is a gradient field. Because it is the gradient of some scalar function. F is called a potential, F is called the vector field. Little f is a potential for big F if big F is just equal to the gradient of little f. Okay, so now if F is equal to F1, F2, F3, this is the vector field, then finding a potential amounts to solving the following equations. We want to find a scalar value function such that F1 is equal to the x derivative of F, F2 is equal to the y derivative of F, and F3 is equal to the z derivative of F. Okay, now, in a sense, this is like finding an antiderivative. But there are two things to keep in mind. One is not very important, but one is very important. So the one that's not very important is that notice that the capital letters and lowercase letters are kind of backwards. So here we're saying capital F is a derivative. Usually in Calc 1, we would say that the lowercase would be the derivative. We would say that little f is equal to big F prime. But notice it's different here. Here the capital F is equal to the derivative of a lowercase letter. Well, that's just something that you have to get used to because we want to use capital letters to mean vector fields and lowercase letters to mean scalar fields. The important difference is that unlike in Calc 1, not all vector fields have a scalar potential. In other words, not all vector fields are equal to the gradient of some scalar field. So for example, in the last set of examples, we looked at these differential identities. We saw that the curl of a gradient field is equal to 0. Okay, so what does this tell us? If the curl of a vector field is not equal to 0, then F is not a gradient field. Because if F was a gradient field, then F would be equal to the gradient of some little f. And this identity would tell us that the curl of F is equal to 0. Okay, so think through the logic there. If the curl of a vector field is not equal to 0, then the vector field is not a gradient field. And again, that's just based on this identity, because if the vector field was a gradient field, then the curl of that gradient field would be equal to 0. Okay, and so the important difference is that not all vector fields are gradient fields. That means not all vector fields have a potential. In other words, that means that not all vector fields have an antiderivative. And that is a different thing than what you saw in Calc 1. So let's very quickly look at this example. So find a scalar potential or show one doesn't exist of this function f equals yz, xz, xy. Okay, so again, we want to solve the system of equations. Yz is equal to fx, xz is equal to fy, and xy is equal to fz. Okay, so let's just look at this. So if we have a function and we take its partial derivative, we get yz. So one f that might satisfy this would be something like x, y, z, because the antiderivative of yz with respect to x is equal to xyz. And notice that if we take the derivative of this with respect to x, we get yz. And similarly, if we take the derivative of this with respect to y, we get xz. And if we take the derivative with respect to z, we get xy. So we would say a potential is f of x, y, z is equal to x times y times z. Okay, but notice that another potential would be this plus any constant. Okay, so when there is a potential, it's not unique, but as we will see, or as you can read about, I don't think we'll have time to lecture about it because we lost a week. That's just going to be my excuse for a lot of stuff. so if you have a vector field and it has a potential, the potential is not unique, but the only difference between any two potentials is going to be a constant. They just differ by a constant. So if little f and little g are both potentials, f minus g is going to be some constant. This is like a constant of integration. It's very similar to what you saw in Calc 1. Okay, now to do this question, find a scalar potential or show one doesn't exist for this function. This is going to take a little more work, and I'm going to do that in a separate video.